Welcome back, and today we're going to talk about this guy, which is an OR. And arguably it's not that exciting because it just says whether or not any of its two inputs or three inputs are high or not. It's exactly as it sounds. And so I've got a couple ORs in here. I might have missed one or two when I was highlighting them, but these are super common and they're available just absolutely everywhere, and they can come in a little bit handy, but honestly, I think today you would have a hard time justifying putting one of these into your circuit just for the fun of it. But let's go ahead and take a look at it, and let's look at some of their data sheets as well and learn about the OR. I printed out a couple pages from the data sheet that we're going to take a quick look at. This is going to be the quad 2 input OR gate, and this is the one that I'm going to wire up today. It's the 74HC32 is the chip number. And as I mentioned, it's pretty straightforward. It's just an OR gate. And if you're familiar with any kind of electronics, you're probably familiar with the way the OR gate works. But let's take a quick look at the diagram here. We've got, because it's a 2 input, we've got 2 inputs. And they're labeled 1A and 1B, and then 2A, 2B, 3A, 3B, 4A, 4B. And then the output is going to be the number y. So 1y, 2y, 3y, 4y. And as you can see, they're just organized based on the kind of the digital logic, and there's nothing overly complicated about it. And if we scooch down just a little bit here, we can see the pinout, and we'll see that it's the first one's here on the top, and then the second one, and they're kind of in order: A, B, Y, A, B, A, B, Y, A, B, Y, A, B, Y. So anyway, a little bit of a funky organization there, but I'm sure they had their reasons. And the most important piece of information is going to be the truth table or the function table based on how the output is going to be. So this is laid out, so it's got NA, so this is going to be 1A, 2A, and so on, and then B, and then this is the output Y. So you can see low, 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 high, 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 low, high, 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 high. So if either of the two inputs is high, then the output will be high. That's the simple way of saying it. And not to be outdone by the 2 input, here's a triple 3 input OR gate. And it's functionally exactly the same. It just has 3 inputs instead of 2. And then if any one of the 3 is high, the output is high. And we take a quick look at the pinout. You can see this one's a little bit different just because in order to fit the pins, we've got the first one here, and then the second one kind of straddles on both sides, and then the third one is over here on the right side. And here's the truth table, and it's like I said, if any one of them is high, the output is high. I guess the only thing worth noting is that it doesn't really matter what A and B are if C is high, and vice versa. So as long as one of them is high, the output will be high, and it won't really matter if 2 of them are high and 1 is low. Here's another one that I've got. Now this actually is a 2 input exclusive OR, or exclusive not OR, and we'll take a look at that here in a few minutes. This is the MC10107, and I think I had 1 or 2 of these in the bundle, but you can see here's the logical diagram, and we'll cover this in a little bit detail when we get over to that chip. And then here is the outputs, and as you can see, it's a triple, so we've got A, B, and C are what's labeled. And the last logical OR one that I have is the exclusive OR, and this is a quad 2 input. So getting back to more of the simplicity, this is the MC5474HC86, or some variation of those numbers. Here's the logical diagram, and so because it's the exclusive, we'll see on the truth table and how that works, but we've got 2 inputs, and again, since it's quad, there's 4 of them, and then 1 output, and it's labeled similar to the very first one that we looked at. So we've got A1, B1, and then Y1. Here are the pinouts, and the pinouts are going to be the same as the regular OR. And most importantly, here's that function table that we've been looking at. Now in this case, if it's low, low, the output is low. And if it's low, high, the output is high. High, low, the output is high. But here's where it gets different, where if it's high, high, the output is low. So as long as the 2 inputs are the same, it will return a low. And if the 2 inputs are not the same, it will return a high. I wired up the very first OR gate, which is going to be on pins 1, 2, and 3 is our output. So let's go ahead and take a look at that. Now it may seem a little bit overly complicated considering the simplicity of an OR gate, and it's a lot of wires, but that's okay. It doesn't matter, mostly because of the switches that I put in. Now we could have just as easily tapped these from high to low on the voltage rail, but by having a nice switch, it gives us a nice little effect. So right now I've got them set up as the white or yellow wire is going to be for the first pin, and the blue wire is for the second pin of the OR, and then the orange is going to be the output, which I've got going through this blue LED through a resistor back to ground. And then the chip is powered over here on this pin on the yellow wire and on this green wire to ground. Now my switches are two positions, so there's the common, and then the middle pin is the 5 volts, and then the right hand pin is ground. So it's normally closed, so it's using the ground, so both of the inputs are 0 or ground or low, which is why the LED is off. So if I press either one of these, the LED will come on, and if I press both of them, the LED will come on. Blah! Now I realize that's probably not all that exciting because it's just an OR, but you could have hooked this up using switches just by putting them in a position to where if either of the switch is on, voltage is running through the LED. Now the thing about using an IC like this is that we can run it at an extremely high frequency. And we can run this up to, a couple megahertz. Actually, I'm not sure what the upper limit on this is, but I have run it on my oscilloscope with a little program from my Arduino, which I can easily run up at about 4 megahertz and confirm that the OR is always correct, and it can clock it in almost pretty much instantly. Will change, and we're going to go ahead and take a look at that next. All right, I've got everything set up on my oscilloscope so we can take a quick look at it. Now I've got a sketch on my Arduino Uno that's allowing me to change the frequency of 2 different PWM signals, and I can do it via this knob right here, and then I've got a couple different ranges as well. I'll do a separate video talking about how I create those. But what I've got is 2 inputs. I've got the yellow and the purple, and those are going to be the 2 inputs to our OR gate, and then the blue signal is the output, which is going to show whether or not it's high or low. Now I'm just going to back this out a little bit so I get it down to a low frequency. Let's see here. We should be able to kind of see the LED flickering. So we're around 120 hertz. And you can see the output is matching perfectly with the 2 input signals. So this isn't that interesting, but let's go ahead and increase that. And I'm just picking up some static from my fingers here. Now I've got this running at about 333 kilohertz. And as you can see, the signals are matching perfectly. You've got the input, 2 inputs, the yellow and the purple, and then you've got the blue, and you can see exactly when it's going up and down. And that's set at 500 nanoseconds per division. So you can see it responds extremely quickly. Let's zoom in a little more. Now we're zoomed in at 50 nanoseconds, and you can see the output is absolutely perfect with the 2 inputs. Now we've got it at 2.66 megahertz, and this is as fast as I can get my little Arduino to screen based on what I've got set up right now. And as you can see, the square wave isn't quite so square, it's a little bit rounded, but you can see it actually follows and tracks perfectly. Let's zoom in a little. And then we're zoomed back in at 50 nanoseconds, and you can see definitely there is a little bit of a shoulder on those, but you can see that it is following the input pretty closely, and you can see when it starts to drop where the signal goes down. Now that we've looked at the OR, let's go ahead and take a look at that exclusive OR, and let's put that on this breadboard instead. On the breadboard, I now have this MC74HC86, and I have a whole bunch of these, and these are those exclusive OR gates, and this is a quad 2 input. So as we saw with the previous one, we've got 2 inputs and 1 output, and as we talked about earlier, here is that truth table. So we're looking at 2 lows is low. If either of them are high, it's high. And then if they're both high, it's also low. So I've got that on the breadboard. Let's take a look. So just like before, if either is on, the LED is on. And if they're both off, the LED is off. I actually have this wired up the same way. 2 switches, normally closed is going to be to ground. And then when pressed, it's going to go to 5 volts. And then switch 1 is the white wire and switch 2 is the orange wire. And then I've got the blue LED through a resistor. So on, perfect. And then if I press them both down, it's also off. So if they're both high, it's off. If they're both low, it's off. Now the reason it blinked right there is just due to contact bounce. I can't possibly get them both down at the exact same time, but a microcontroller would be able to do that. So anyway, that's a look at the exclusive OR gate. And that concludes our look at the OR gates. I really thought that was interesting when we took them up to 2+ megahertz and watched the sine wave be able to still maintain that on-off on those OR gates. I'll try to figure out a better way to record video from that oscilloscope. I think there is a way to actually do some video capture on it. I think I'm going to do one more video on some additional logic gates. I've got some ANDs and a few others, and then we'll move on to some of the more interesting chips that are very custom based on what they're doing. And those ones might be a little bit more complicated, and we might not have nearly as success as what we've had on this one. So until then, I'll see you next time.